Hi all. Yeah, I forgot to apologize for not doing this in Camtasia. Just not enough time. So sorry for the non-professional presentation here. Okay, so topic 2 is capacitance, not capacitors, capacitance. So let's take a look at this. First thing, just to remind you, we looked at the pictures for the capacitance drawn into the small signal models last time. And again, this is the model that we used for the MOSFET at first. Totally was useful because all we were looking at was gain. Now we're starting to talk about moving signals, so we have to change the model so it's appropriate to what we're doing, and now we have this model with the capacitances drawn in. Okay. So just to remind you that things are modeled in various ways, and those models are useful when you're doing circuit analysis. And you always want to choose. You don't have to, but to make your job easiest, you always want to pick the simplest model that is going to allow you to analyze that circuit. And on printed circuit boards, really a transistor is very often used as a switch. So all you really need to know is if it's conducting or not conducting. You don't need to care about resistance. You don't need to care about capacitance or anything like that. So it's modeled as this. Okay. When you get to the digital realm, you're worried about delays. And a delay on a node is directly related to RC time constant. And so now, when it's conducting, when a transistor is conducting, you need to know its resistance. And notice that I didn't say resistive behavior, I said it's resistance. So in the digital realm, what you do is you find the voltage across that transistor and the current through it and say, hey, I know what resistor that would be. Which is different than what you do in the small signal realm, where you say, okay, if I change the voltage a little bit, how much does the current change? So again, in the digital realm, you just take the voltage across the transistor, the current through it, and you say, hey, I have a resistor. This is behaving like a resistor, like a real resistor of this. And small signal, it's change in voltage over change in current. Okay, so in the digital realm, now you need to take into account resistance. Let's say you're analyzing some circuit like this, and you want to know about this first inverter right here. And if you're analyzing this first inverter, you don't care what the second inverter does. This could be any circuit at all. You don't care what it does. You're trying to figure out how fast this node on the output of this first inverter is changing. Okay. To do that, all you really care about is the capacitance you see being provided by this second inverter. You don't care what it does. You just care about how it's going to affect this node, which the way it affects this node is by contributing capacitance to it. So when you model it, all you need to do is that. That's a good enough model for this whole circuit right here, because all you care about is how much capacitance or resistance it's going to contribute to this node. And you know the resistance is infinite, so it contributes no resistance, but does contribute to capacitance. And I hand waved a little bit on that. At high frequencies, you see this capacitance as a resistance. Okay. And then really, if you're in the digital realm, when you're trying to find the delay on this node, what you do is you take this transistor, you say, oh, I've got a voltage across it, I see a current through it, I can model that as a resistor. I know this second stage right here, all I care about is the capacitance, so I can just turn that into a capacitor. Now this is the circuit you have to analyze instead of this whole thing. So remember, choose the simplest model that you need to do your analysis, and it will make your life much easier. Okay, and we've figured out, we've done all this, so did this. and figured out where all the capacitance are. This is where I have all the equations and how to calculate the capacitance for a MOSFET. And then I also did that for BJTs. One thing I didn't do in class for BJTs is talk about the equations. And so I gave you kind of a summary of equations here. And again, these equations, there are some extremely complicated equations. The equations that SPICE uses are extremely complicated. For humans, on paper, when you're just trying to get an idea of a value, you don't need those complicated equations. Some of the stuff you did in 306 was probably horribly complicated. I know when I took my solid state circuit class, they had us doing some crazy calculations. So yes, those are probably more accurate, but what these hand calculations are for are to get a good enough ballpark figure, and then you can go in and simulate to get those more exact values. Okay. And again, when you're working out the capacitance for a BJT, I'm assuming that you can't really see these equations very well, but some of these values are process dependent. In other words, you know, which company fabricated that transistor, and that information, a lot of it can be found in the model file. So here's your CJC, a CJE. If you go back to the equation, here's your CJE right here. CJE, CJC. I don't see the CJE. It's the CJE. Yeah, I can look at this later. But CJE. Oh, okay. I went for the base. To the base source, okay, base emitter. Anyways, so yeah, so any missing values in here, can go over here to the model file and figure them out. And again, do an approximate, very approximate calculation of the capacitances between the base emitter, the base collector, and the collector substrate for BJT. Okay, and I did do a couple of calculations here, and for this particular process right here, we got in the picofarad. I got in the picofarads. And you say, what? That's not much. But yes, that is why we are in lab. We are adding 2 capacitors to our design to try to bring down those poles to a frequency that our oscilloscope can see. Actually, these poles, the natural poles and zeros, are probably going to be way too high, at way too high a frequency for us to observe on our oscilloscope. But one interesting thing here is that the capacitance contributed by your breadboard is much larger than your transistor, probably. So you may be getting some of the poles from your breadboard if you keep going up before you get to the actual poles contributed by the transistors. Okay. So we're finally getting to topic I promised at the beginning of last video, actually. We're just getting to capacitance. Okay, and again, I said capacitance, not capacitors. So let's look at this. Got these capacitances that I drew in here. Yeah, now we've got a model for them. One rough thing is, let's make this blue, purple. Let's do, what's a color that you can see? How about green? If this was, let's say this is a common source with a passive load. You know, you'd have, if this is a common source with a passive load, you'd have this, and this would be connected to ground. Oh, bulk is, let's connect that to ground too. Okay, so I just changed that to a small signal model for middle frequency. If you add the capacitances, now this is considered a model for middle frequencies. If I added inductance, then this would be for high frequencies, but add capacitance to do analysis for middle frequencies. And if this was a common source with a passive load, the green, I'd add the green right here. And what you'll see here is, well, if you look at this capacitance right here, this is gate drain overlap right here. Whoops, oh, I did it wrong. Oh man, I have to go back and do that. Okay, gate drain overlap. I should make a list of all my mistakes. Gate drain overlap in first video. Okay, yeah, so this gate drain overlap right here, it makes it so again we're putting these capacitances in, and then we're going to do some analysis, circuit analysis. And if both sides of a capacitor are moving, it makes the calculations really complicated. So let's see what I'm saying here. Let's get rid of something here. Let's get rid of this. So the circuit that I'm looking at right now is a common source right here, and the capacitance we're looking at here is from the gate to the drain. So it's from the gate to the drain. So if you drew it in on the regular circuit, the regular schematic of that, that's where that capacitance would be. Now if you look at this, if I move VI up, if I move the input voltage up, if you think about it, what happens to V out? V out goes down. So if you look at this capacitor right here, this capacitance right here, both sides are moving. So you have one side going up, one side going down. Okay. This makes for a really horrible analysis. So if there was some way we could get rid of this capacitance in our model, that would really make our life easier. Let's see how to do that. I actually gave you a picture right at the end of lecture on Wednesday that is kind of the secret to this, and I'm going to do it with my hands in front. I don't have a cup here, but let's say, actually I do. It's not a very good cup. So here's a cup. All right. Now, when you think of a capacitor, you've got Q equals CV. You've got Q equals CV. And this is another one of those equations where it's easy to have misunderstandings. What's really happening is this is delta Q. It's the difference in charge between the two plates. So it's the difference in charge between the two plates. And I find the computer. Okay. This is the difference in charge between the two plates. Not just the charge, it's the difference in charge between the two plates. And that's why when you move one side of a capacitor, so if you have a capacitor, and you move one side, the other side, if you move one side instantaneously, the other side has to change instantaneously, because it's the difference in charge. It's the difference in charge between these two plates that gives you your voltage. And if you move this instantaneously, that charge doesn't have time to go anyplace. So the difference in charge between the two plates doesn't change. Therefore, the voltage between the plates doesn't change. And if the voltage between the two plates doesn't change, this side has to move the same as that side. Or the other way around. This side has to move the same as this side. Okay. So you've got your Q equals CV. Okay, so here's your capacitor. This cup is too big. How about a bowl? There we go. Yeah, I got a bowl. Okay, so here's your capacitor. Here's one plate, and the amount of water in this bowl. This isn't working. I should use a cup. The amount of water in this bowl, that is your charge. Okay, and you can think of the difference in voltage between the two plates is this is the bottom of the water and this is the top of the water. Okay, now when I go back to the okay, so if I'm pouring water into this cup, somebody asked me, how big does this cup look? Let's say I just have it sitting on the table and I pour water into it. I'll pour a certain amount of water into it and I'll see the level of water that on my side, because I can just see the top of that water there. I can't see the bottom of the cup. So I'll pour some water in there. I'll be watching the top of this, and I'll see it eventually come up, and I'll say, okay, I know how big that cup is. Okay, and it's however much water I poured in there, right? Okay, so let's look at another case, and let's say I have this cup. Same amount of water now. Same amount of water. And let's say I move the cup down as I'm pouring water into it. So I'm pouring water into it, but I pull the cup down. And then I say, well, I poured this much water into it, but the water level, since I'm moving this down, and let's say I can only see the top of that water. If I'm moving this down and I'm pouring water into it, I'm going to see the water level rise much slower. Okay? So pour water into it, but if I move the cup down as I pour water into it, but I can only observe the top, that top of that water. It looks like this cup is filling up much more slowly. Okay, same thing with a capacitor. If I have a capacitor and I'm moving the voltage down on the other side of the capacitor while I'm putting charge onto it, I'll see this voltage rise much more slowly. Okay, so if I have a capacitor and I'm moving down the voltage on the other side of the capacitor, and I'm putting charge onto this side of the capacitor, but I can only see this side of the capacitor. I'm putting charge onto there, and I see the voltage rise slower, then I'm going to think that's a much bigger capacitor, because I put a whole bunch of charge on there, but the voltage didn't change very much, from my viewpoint. Okay. All right. So, right. So, yeah. So, the short version of that is, if the other side of the capacitor is moving, then from my side, if I can only see my side of the capacitor, I'm going to see a different sized capacitance than it actually is. So let's look at, just a quick review, because we did this in class, the partial lie version, and that's without taking into account the other side of the capacitor moving. Here's a common emitter going into another common emitter, and we're looking at this node right here. So to find the capacitance at that node, you stand on here and I see the wire going in three directions. I see it going up, down, and towards Q3. So I see it going up to Q2, down to Q1, and over to Q3. So eventually I'm going to have to check out all three wires, but what did I do first? So I go up, I see the collector. So I go up, I see the collector. So let's go over here. I know that if I'm sitting on the collector, I see two capacitances. I see the collector to substrate capacitance, and I see the collector to base capacitance. Oh, I had that picture over here better. Okay, let's do that. So if I'm at the collector of Q2, I see the collector to base capacitance, and I see the collector to substrate capacitance. So here's CCB2 to CCS2, collector base, collector substrate. Okay, that's all the capacitance I see looking up. So now I'm going to go down. I hit the collector of Q1. So again, I'm sitting on the collector, so I see collector substrate and collector base capacitance, CB1, CCS2. And then, so now I've done this wire, I've done this wire. I have one more wire to go. I have to go down all possible paths. And I go to Q3. And if I'm on the base of Q3, I see a base emitter and a base collector. So base emitter, base collector. And those are all the capacitances at this node. I'm just trying to find the capacitance right now. Okay. And you didn't have to do small signal analysis. You didn't have to do anything. You just had to follow all the wires in all the directions and put yourself on this picture right here to see what capacitors you see. Okay. And you get all this. Okay, great. All right, that was easy. And same for MOSFET, except the capacitances, there's a few more capacitances here. So again, you have to go in all three directions. So let's go up, you hit the drain. So let's go sit on the drain over here. I see two capacitances connected to the drain. One is the drain bulk, and one is the gate source overlap. So here's the gate drain overlap and the drain bulk. And then if I look down, I see the drain of M1. So I get the same thing. I get the drain bulk of 1, and I get the gate drain overlap of 1. And then the last one is I hit the gate of M3. Assuming it's in forward active, I'm going to get the gate source overlap, gate drain overlap, and then the gate source, which are those electrons collected over towards the source. Okay, again, not so bad. Okay, that was the line version, because you know that if you are on V in and you move V in, V out's going to change. This capacitance is going to change right here. Plus also this signal goes over to M3, and that means that the gate of M3 is moving, which means V out is moving, which means the capacitance between the gate and drain of M3 also has both sides of it moving. Okay, so again, those two capacitances, both sides of them are moving. Right here you have V in and Vn. The capacitance between here has both sides moving. And again, from the gate to the drain, this capacitance also has both sides moving. Okay. Alright, so remembering that cup, that if the cup is moving down and I'm pouring water into it, I see the water rise at a slower rate, which makes me think it's a bigger capacitor. Let's see what happens here. Okay, that's saying about the cup, right? So let's look at this. Let's look at the from Q3 to V out. So the base of Q3 to V out. Let's see what happens here. Okay, there's going to be some charge across that capacitance, the base collector capacitance. There's going to be some charge across it. That's the difference in the charge between the plates, and that's going to give you the voltage across that capacitance. Okay, so let's see something here. If I change, we'll call this V in for right now, not this one, but the base of Q3. Let's take that as V in. So the base of Q3 is your V in right now. Okay. What you'll see is, okay, you know that this capacitance right here times the change in voltage will give you the change in charge. Okay, and this change in voltage here is delta V in, and the change in that voltage is delta V out. You know that this is an amplifier, so it has a gain of AV, and so you know how much V out is moving is AV times V in. The change in V in times the gain gives you how much V out moved. Okay, and now you can factor out the change in V in, and you get a 1 minus AV here. And AV is actually negative for a common emitter or a common source. So this is actually going to come out to 1 plus the absolute value of the gain. Alright, so let's see what this has said. It says if you change the base voltage at Q3, that's what this is. This is this Vn right here. Okay, my computer's not gonna, oh, there we go. Let's make this Q3. 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 Okay. What this says is, if you change the base voltage of Q3, you get it, okay, we change the voltage across, change the base voltage at Q3. What you actually get is a change of voltage across this capacitance right here of that change in voltage times 1 minus AV. Okay, see if I can say it better this time. What this says is if you change V in by some amount, what you actually get is a change of voltage across CBC of V in times 1 minus AV. So the voltage change across the capacitor is this whole thing, this delta V in Q3 times 1 minus AV. That is the change in voltage across the capacitor. Alright, so let's look at let's go one step further. Okay. Now, again, what we said is if there's a change in voltage here of delta Vn, you actually get a change of voltage across this capacitance of Vn times 1 minus AV. So what you can do is, instead of, you can get rid of this capacitor by saying, hey, I know if I move it this much, there's going to be that a particular amount of voltage change across there. Let's see. Okay, so let's look at this. We know that if I change V in this much, I get a change of voltage across CBC of this whole amount. But you can also say that's the same as having a change of V in across a capacitor of size CBC times 1 minus AV. Okay, this is a lot like how we did that shortcut for Rn of degenerated common emitter or a emitter follower. Okay, so what we can say is that you'll get the same change in charge for a change in voltage of delta Vn times 1 minus AV across a capacitor of size CBC as you will get for a change of voltage of delta Vn on a capacitor of size CBC times 1 minus AV. Confusing? Okay, all I'm doing is moving the brackets here. I know I get a change in charge for this change in voltage across this capacitance. So what I'm saying here is I can get that same change in charge by having this change in voltage across a capacitor of this size. Okay, getting closer here, So now, okay, so now what you can say is, all right, so I have a capacitance here. I know what the change in voltage across it is. Turns out that I can move that capacitor. I can move that capacitance to ground as long as, since I know this node right here moves delta Vn. Remember, let's go back. Remember, I can get the same change in charge on that capacitor if I have a change of voltage of delta Vn times your CBC times 1 minus AV. If I have a capacitor of this size and a change of Vn across that capacitor, I get the same change of charge as I have if I have this capacitor with this much change in voltage across it. So what you can do is get rid of this. Remember, this has the other side is moving on this. What you can do is you can replace that with a capacitor where only one side moves less, but you just make this capacitor bigger. And how much bigger? It's 1 plus AV times CBC. This is going longer than planned, but it's okay. All right, so moving on. Okay. And this is called Miller capacitance. Usually Miller capacitance is for a common emitter or a common source. Whatever I'm saying about BJT is still true for MOSFET. So common emitter, common source from its input to its output. And that capacitance right there gets multiplied by, it always gets multiplied by 1 plus the absolute value of AV. So take whatever this capacitance value was before, put it down here, and multiply it by 1 plus absolute value of AV. Okay. So let's look at what happens to some of the other capacitances. Let's look at going back this way. So remember, we're looking at this node right here. We're looking at this node right here, which I called VN last time. There's a capacitor from Vn to Vin. I hope it's drawn on there. Let's draw that on there. Pointer option, 0 pin. So there's this capacitance right here. That's C, BC, or C mu. Oops, dog alert. Right there, but we're sitting on this node right here. Now, if this node moves right here, this node moves too. But let's see, if this moved, let's say 1 volt, let's say Vn, let's say Vn, well, the birds got a little bit quieter, but now the dogs are going crazy. Okay. If this node moved 1 volt, the question is how much would Vin move? Remember, this is the output of an amplifier. So it takes whatever is on the input, multiplies it by AV, and shows up on the output. So if the output moves 1 volt, then the input actually moves 1 volt divided by AV. So if this moves 1 volt, this actually moves 1 volt divided by AV. And let's say the gain is 100 here. That's, if this moves 1 volt, this moved 1/100th of a volt. Okay, so this CBC, you're saying, if you're sitting here, yeah, both sides are moving, but it turns out since this side moves so little, moves 1 over AV times as much, that most people just consider this as a ground. Even though the other side's moving, saying it's moving so little, that's close to a ground. If you want to be a little more accurate, what you do is you say, the other side, yes, if I move up by 1 volt, the other side moves down by 1/100th of that. So really it's 1 plus 1 over AV, but that approximately just equals, you can pretty much just kind of consider that as 0 and call it ground. Okay. So looking forward, if you're sitting on the base of Q3, you see an increased capacitance of 1 plus AV, the absolute value of the AV. But if you're sitting here and you're looking, you're on this node and you're looking back to the other side, so the input of the amplifier, then the other side of the amplifier looks like it's not moving very much. It's just moving 1 over AV. So, and you can kind of consider that as ground. Okay. Right. So notice that these are numbered here. Where's 1? Okay. Number 1 is kind of skip that, but that's the easiest case. That's where you look at the other side of the capacitor and it's not moving. So let's look at that. Let's look at, you know that if you're on the base here, you see a base emitter capacitance, CBE or C pi. And that capacitance right there, if you're sitting on Vn, so if this is Vn, this side, yes, this side is moving. but the other side of the capacitor isn't moving. So whatever the value of CBE is, that's what it is. That's the capacitance you see on this node. Okay. So that's case one, where the other side of the capacitor isn't moving, then you just see that capacitance. The second case is this Miller case, where you can ignore this capacitance, but add a capacitance down to ground and multiply it by 1 plus the absolute value of AV. Now we're on to the third, which is where you're on Vn and you're looking backwards. You're on the output of an amplifier, and you're looking back to the input. You have a capacitance between the output of that amplifier back to the input. Then you kind of have that first case again, where the other side is basically ground. So you just, when you add a capacitance to this node, it's just a CBC. Or if you really want to put details in there, it's 1 plus 1 over AV. The capacitor looks 1 plus 1 over AV bigger than it actually is. Okay, so that's case 3. I have 1, other side connected to ground, 2, other side connected to the output, from the input of an amplifier to the output of an amplifier. 3 is from the output of the amplifier to the input of the amplifier. And then you have some special cases. And let's say here's your V in, here's your V out. The question is, what about the base collector capacitance right there? So there's a capacitor from here to here. Question is, how much bigger does that look? This is tricky. What you have to think about is, if I move this, let's say I move this up delta V, question is, how much does this node move? And this is tricky. This is tricky. Look at it, if you look at this node, you know this right here, that's about a VB on. And this node right here, that's a fixed voltage. So this right here, this is not going to change very much from V bias 3 minus a VB on. That node is just not going to change very much. But if you change the voltage here, you're going to have a change in current. So if you change this by delta V, you just change the VBE of this transistor by delta V, that's going to cause a change in current through here. If there's a change in current through here, there's a change in current through here. If you ignore base width modulation and assume these are all inactive, if you change the current through there, you need to have the same change in VBE on the second transistor. Okay? So if you change the current through here, you're changing the current through there. If the base is fixed, so if you're changing the current through there, now you have to change the VBE to accommodate that new current, which means you have to change the VBE delta V, which means this node right here has to go down by delta V. So you change this, you raise this delta V, that changes the current through here, which also changes the current through here, which forces a change in VBE of delta V. Since the base is fixed, you increase the VBE here, you have to increase the VBE here, but the base is fixed, so you have to drop the E to increase the VBE. So what you see here is if you raise this delta V, this node is actually lowered by delta V. So the net change in voltage across this capacitance, the net change in voltage across this capacitance is actually 2 delta V, which means that capacitor, that capacitance right there, the capacitance on this node looks twice as big. If you're sitting on V in and you move this side delta V, the other side moves delta V also. If you're sitting on V in, this capacitor right here looks twice the size. You moved your side delta V, the other side moving the opposite direction in delta V. You've got actually twice the voltage change that you've given it across that capacitor, so the capacitance looks twice as big. So what you can do, options. What you can do is, instead of putting a capacitor to Vx, what you can do is put that will give you the exact same effect as trying to figure out this complicated capacitance here. There's this complicated capacitance here. Both sides are moving. So now you have a much easier capacitor. You have a capacitor to ground to model with. Okay, let's look at and this is the last one. This is the last one. And now let's look at V in. Oops. Let's look at V in into V out. That's this capacitor right here. This capacitance right here. All right. This is a follower. So let's say again, you're always looking from. You're looking at both ends of the capacitor and seeing how much the voltage on both sides move. If I move this delta V up. Remember, this is a follower. What happens to the voltage at that node? I claim that that also goes delta V up. This is a follower, so if this goes up, this goes up. And I put a transistor down here intentionally just to say that this is pretty much a perfect follower right here. This is a perfect current source, and this is going to be a perfect follower. VBE is going to be constant. Okay. Now, if this side of the capacitor moves up by delta V, and this side of the capacitor moves up, so this side of the capacitor moves up by delta V, and this side of the capacitor moves up by delta V, what's the net change in voltage across this capacitor? Capacitance. It's 0. Okay. If there's no change in voltage across a capacitor, how much charge goes on to the capacitor or off of the capacitor? 0. So this capacitance right here, because there's no change in voltage across that capacitance, there's no charge going on or off of it, which means it contributes nothing to the behavior of your circuit, and you can just get rid of it. So yeah. So if there's no change in voltage across the capacitance, you get rid of that capacitance from your model. And so even though there's a capacitance there, because both sides move, you ignore it on your final analysis. Okay. So that's the capacitance. I'll because the R is quick. Remember, we're trying to find our time constant, which needs an R and a C. I've given you all the tools to figure out what the C is. Now to find the R at a node. In the same way that you went in all directions to find your capacitance, if you're sitting on this node right here, you go in all directions. I see a wire going in 3 directions here. I see one going up to the collector of Q2, down to the collector of Q1, and over to the base of Q3. You need to follow all 3 wires. You need to follow all 3 wires. And it turns out that all of those resistances, and you use small signal resistances. I have to say that about 5 times, so excuse me, but to find the resistance, you use the small signal resistances. Use the small signal resistances, anyways, and put them all in parallel. So if you go up and you hit a collector, what do you see? You see RO of Q2. Okay, I'm done with that wire. Now I go to my second wire, and I have 3 wires to do here. Go down to my second wire, it's the collector of Q1, so up, it's RO of Q1. And then I go over here, and I'm done with these 2 wires. I still have this 3rd wire to follow over to the base of Q3, and that R in is R pi of Q3. And the R at this node is just a parallel of all 3 of those. Okay. if this had degeneration here, then you'd have r pi plus 1 plus beta times re. If there was some other, like if this was flipped, then you'd see 1 over t. Yeah, you know, what you need to do for each case, you know, that each case will be different. If you follow all of the wires from the node that you're looking at, and then put all of those resistances that you see, small signal resistances that you see, in parallel. Okay. For a MOSFET, do the same thing. Here you hit the drain, and that's RO. Look down, you see the drain, RO. This way you see infinity, and so it disappears, and you just see the ROs for the two. Okay, and then the quick way to find the pole is now you have your C. So it's all the C's at the node add, all the R's at the node are put in parallel, and now you have a C and R. Now you have a pole for that node. So for a BJT at node Vn, we found our capacitances. This is a lie. Got to fix this. I will post new slides because remember, we don't have the 1 plus AVs in here. I have to add those. I will post the fixed slides in a minute. The collector base, well, how about this? Okay, you know, anything going from the base to the collector, well, actually, I should probably do this a little more carefully. What do we have? I'll come back and I'll fix these slides. But that, you find your C and your R, you multiply them, and you've got your pole. And if you notice that I kind of tried to force you to have two gain stages. That is so you would have two nodes and you would have two poles. So you have a pole on the output and you have a pole on the output of your first gain stage. And that was intentional. And we'll see why that is when we start talking about feedback. We've got almost all of the frequency response stuff covered now. And now it's pretty much practice, and that's what I'm going to give you the homework for. I might also make a video just going through a number of problems, so you can, because I think that would be helpful since we don't have time in class to do that. All right, so that's how you find your R's and your C's, how you find your poles after you found your R's and C's. That's how certain capacitances can either be ignored or have to be multiplied by some value. And go back, and if you're uncomfortable with Bode plots, I'm totally happy to have a separate session talking about how to put those onto a Bode plot.